Okay, so finally we'll compare all the system T, and this is IT. Okay, first, over-damped system. Okay, over-damped system will reach the peak value slowly, then it will decrease. Critical damped system will reach the peak little bit quicker as compared to the over-damped system, then it will decrease. Okay, this is over-damped. Over-damped. Then this is critical damped. Again, exactly you can also find out this value by doing the differentiation. Okay, once if you do the differentiation and make it equal to 0, okay, you can get the exact value of T also, at what time it is reaching the peak. Okay, so if it is under damped system, okay, it will reach much quicker as compared to other systems, but it will not settle down. It will be getting oscillated like this. Okay, it will get oscillate. Okay, so this is under damped system. Okay, under damped system. Okay, finally you should know what is alpha. Alpha means R by 2L. What is omega? Omega means 1 by square root of LC. Okay, so if alpha is greater than omega, over damped. If alpha is equal to omega, critical damped. If alpha is less than omega, under damped. So for a over damped, alpha is greater than omega naught. Here alpha is equal to omega naught. Here alpha is less than omega naught, where what is alpha? Alpha is equal to R by 2L. What is omega? Omega naught is 1 by square root of LC. So exam point of view, these values are important. You have to remember this. Okay. So next we'll see the parallel RLC. Parallel RLC. Okay, so here I'll go a little bit quicker. Okay, so R, L, C, and again here the assumption is already the capacitor is having some initial energy, some initial voltage. That voltage is V. Okay, here C, L, and R. Okay. Then we write the KCL, Kirchhoff current law, at this node. Okay, the current leaving the junction. Okay, from this junction is 0. Current leaving the junction is equal to 0. That means what is the current leaving here, current leaving here, current leaving here. So again, once if this is V, the same voltage will appear across here. Okay, because this voltage is also same as this voltage with respect to ground. Okay, it's a nodal voltage, because this point with respect to this point with respect to this point, again both are like a parallel. Okay, so the node voltage is same as the voltage across the capacitor, and the same voltage will appear across the inductor and also across the resistance, because when you have a parallel elements, the voltage across the elements are same, but this voltage is not a constant voltage. This voltage will decrease over a period of time. Okay, so initially you may have a voltage, some voltage, say for example 10 volt, but over a period of time it may decrease, because this is not an independent source. Okay, this is the capacitor with the initial voltage. When a capacitor is having some initial voltage, once if it is connected with the circuit, then current starts flowing, then again charge is getting depleted. Finally there will not be any charge across the capacitor. So you have to understand that this voltage will decrease with respect to time over a period of time. Okay, so finally the voltage across the capacitor will be 0, because this is a source free circuit. Okay, so you write the KCL, Kirchhoff current law, at this node. KCL. Okay, so current going through the resistor is voltage divided by the resistance, V by R. Current going through L is 1 by L integration V dt, and then current through the capacitor I is equal to C dV by dt is equal to 0. Okay, then again you do the one more differentiation. Okay, then C d square V by dt square. Okay, 1 by R dV by dt. Okay, V by L, this is L. Okay, V by L is equal to 0. Then you take the Laplace transform, C S square Vs. Okay, then 1 by R 1 by R Vs, and then Vs by L is equal to 0. Okay, you take that Vs outside. Okay, Vs outside, then we'll get Cs square 1 by R 1 by L equal to 0. Okay, Vs S square 1 by Cr 1 by Cr 1 by Lc. Okay, so finally you are getting S square 1 by Cr. Here we'll get 1 S. Okay, one differentiation is there, means 1 S will come here. S. Okay, S square S by Rc plus 1 by Lc is equal to 0. Now what is the roots? S1 comma S2 is equal to minus B plus or minus B square minus 4AC divided by 2 divided by 2. Okay, again I will take these two upward. So S1 comma S2 is equal to minus 1 by RC plus 1 by 4RC, not 4RC, it is 2RC, 1 by 2RC whole square minus 1 by square root of LC whole square overall square root. Okay, this is 1 minus 1 by 2RC. Okay, just I am taking these two upward. Okay, I am taking these two upward. Okay, so again, what is the change here? This I'll call it as a alpha. Okay, this is alpha square, again minus omega naught square. Okay, so the all the formats are same. Okay, same format we are getting, but the alpha value only different. Okay, in the previous case we got what, R by 2L, I think. Okay, what is alpha in the previous case? R by 2L, but in this case we are getting alpha as 1 by 2RC. Okay, that is the only difference. Okay, and again omega naught C, omega naught is equal to square root of LC. So whenever you have a parallel circuit, okay, your alpha is 1 by 2RC. If it is a series circuit, R by 2L. Okay, the difference you should know. And again omega naught is same for parallel as well as series. Okay, because that we have seen it in the resonance circuit itself. Either you take series resonance circuit or parallel resonance circuit, the omega naught is always same. Okay, now the case 1, if alpha is greater than omega naught, again we know once this is over damped. This is over damped. That means what? 1 by 2RC is greater than 1 by square root of LC. Okay, then that means what? Two roots are negative, and also they are real and unequal. They are not equal. Then what would be the response? Okay, the response means in this case, what is the response? I think is it VT? Okay, so yes, finally Vs. Okay, so finally the response means like voltage, how the voltage across the capacitor is getting decreased. Okay, that is Vt is equal to A1 e power S1t and then A2 e power S2t. Again here A1 and A2 is a constant. Okay, then case 2, if alpha is equal to omega naught, then this is critically damped system. That means 1 by 2RC is equal to 1 by square root of LC. Again, two roots are negative and real and equal. Then what is the response? E power minus alpha t. Again, you can put like this also, no problem. A1 plus A2t or A1t plus A2, both are okay. So next case 3. If alpha is less than omega naught, under damped, under damped. That means 1 by 2 RC is less than 1 by square root of LC. Okay, now two roots are complex. So our complex conjugate with the negative real part, with the negative real part. Okay, so the voltage across the capacitor Vt is equal to e power minus alpha t A1 cos omega dt plus A2 sin omega dt. This is the response. And again here we know omega d means omega naught square minus alpha square, where omega d means natural frequency, sorry, damped frequency of oscillation. Omega naught means natural frequency of oscillation. Okay. And again the same diagram will get here also. Okay, so again finally the same diagram we will get. But instead of R by 2L, we'll get 1 by 2 RC. Okay. Okay, so here instead of alpha will get 1 by 2 RC. Okay, that is the only difference. Again, rest of the things remain same. Again, here instead of IT, this is Vt, that means voltage, how the voltage is getting decreased. Okay, so everything else is same. This is Vt, and again alpha is 1 by 2 RC, omega naught is same. Okay, so finally for series circuit, alpha is R by 2L. For parallel circuit, alpha is 1 by 2 RC. And again, you should know these conditions. Okay, when alpha is greater than over damped, when alpha is equal, critical, when alpha is lesser, then that is under damped. Okay, now we'll see one problem related to this. Find the nature of the response of IT. Okay, so first the circuit is connected like this. 1 ohm, 1 Henry, 1 Faraday with a 10 volt. So suddenly at t is equal to 0, they are closing the switch like this. In such a way they are disconnecting the source. Okay, that means what? Before t is equal to 0, this RLC is connected with the 10 volt voltage source. Now again the options are given like this: under damped and over damped and critical damped. Okay, and undamped. Okay, undamped. Okay, what is the solution? Okay, now we have to understand here. See, first RLC is connected with the 10 volt source. That means what? Again, we do not know at what time it is connected, but we'll assume that long before it has been connected. Okay, so once if it is connected like this, then just before the switching, the circuit will be in steady state. That means what? The inductor will be short, capacitor will be open. Then what is the voltage across the capacitor? Okay, is the VC0 minus is 10 volt. Okay, that is same as VC0 plus. Okay, that means what? The capacitor is having 10 volt. So the moment you close the switch like this, okay, you are disconnecting the source. Now the circuit will be like this: R, L, and C. So, but the condition here is the capacitor is having some initial energy. Again, my question is whether the inductor will have any initial energy at this time. Anybody? Okay, now at t is equal to 0 minus, okay, what is the nature of the circuit at t is equal to 0 minus? Okay, I'll draw the nature of the circuit at t is equal to 0 minus. Okay, this is the nature of the circuit at t is equal to 0 minus. Now, this is everything is 1 ohm, 1 Henry. Okay, again at t is equal to 0 minus, this is at t is equal to 0 minus, this is the nature of the circuit. Then what is the energy in the inductor at t is equal to 0 minus? Anybody?
No, sir. No energy.
No energy, because at t is equal to 0 minus, the voltage across the capacitor is 10 volt. But what is the current across the inductor at t is equal to 0 minus? 0, because circuit is open.
Zero.
Once the current is 0, then the energy in the inductor at t is equal to 0 minus is 0. Okay, 0. So that means what? Finally, in this circuit, the capacitor will be having some initial energy, some voltage. Okay, so that's why we start our discussion like that. So once if it is a source-free circuit, R, L, and C, then this capacitor will be having some initial energy, but not the inductor. Okay, so now this is the source-free circuit, but the capacitor is having some initial energy. Okay, some initial energy. This is 1 ohm, this is 1 Henry, and this is 1 farad. Now, what is the nature of the response? Okay, so there are 3 varieties are possible. One is under damped, another one is over damped and critical damped. Undamped means what, sir? Undamped means continuous sinusoidal. Undamped means continuous sinusoidal. Okay, so definitely the fourth option is not possible, because it is having some initial energy. With some initial energy, with some finite energy, it cannot produce sinusoidal waveform like this. Okay, so if it is able to produce like this, and this is like undamped system, undamped, and that too with the resistance in the circuit, you cannot produce this nature. Okay, if the resistance is not there, okay, you can produce this kind of waveform. Okay, so once, see what will happen when resistance is not there, what will happen? This is a inductor and another one is capacitor. Okay, so for example, if the capacitor is having some initial energy, okay, capacitor is having some initial energy. So again, in the circuit, you see there is no resistance. Okay, so once if the capacitor is having some initial energy, what will happen? Initially, it will try to give the energy to the inductor. Later, the inductor will try to give the energy to the capacitor, and again capacitor to the inductor, because inductor and capacitor can store the energy. Okay, can store the energy. That means what? When the energy is more with the capacitor, it is giving the energy to the inductor. Once if the inductor is having energy, more energy, then it is giving to the capacitor. It is like, okay, so that's why it will produce some sinusoidal waveform. Okay, so the energy is going in between the inductor and the capacitor. Again, our assumption is it is like pure inductor and capacitor. Then there is the possibility that you will get undamped signal. Okay, so continuous sinusoidal signal, that signal is called undamped signal. But once if you have a resistance in between, okay, once if you have a resistance, then what will happen? Okay, so see, if you are having resistance in between, okay, inductor is there and resistance is there, this is capacitor. Again, this is the example for series RLC circuit. Okay, this is L, R and C. Now what will happen? From the capacitor, the energy goes to the inductor. From the inductor, the energy comes to the capacitor. But in this process, some energy is lost through the resistance. So that means what? Initially, it will be like this. Gradually, it will decrease. Finally, it will reach 0. Okay, so that's why this is the process that is happening. So whenever you have a circuit like this, once if you have some initial voltage across the capacitor, okay, so the charges will try to go from one end to another end. During that process, it will there will be loss of some charges. Okay, because the resistance will not store the energy; it will simply dissipate the energy. Okay, so then again, what, the charges are getting decreased. Okay, so that's why the amplitude is getting decreased over a period of time. This is called under damped system. This system is called under damped system. Again, this is also like sinusoidal, but its amplitude is getting decreased. Okay, this is under damped system. Again, this will not happen all the time. It is also really depends on what is the value of RLC. Okay, if value of RLC in such a way that, then you'll get this waveform. But if it is in different manner, there is another possibility is there. Okay, it will increase the peak, then it will suddenly it will increase the, okay, the value will increase gradually, then it will reach the peak, and then slowly it will go to zero. And again sometime it will reach very faster, and again it is also going to zero. So again these cases also possible. It all depends on what is the value of RLC. But one thing is not possible here, this is not possible. Okay, this is possible only when if your R is zero. If your R is zero, this is possible, but R is not zero. Here they given some R, that means option D is completely not possible. So any one of the option A, B, C is possible. So that means we have to really take the help of that formula. What is that formula is telling? Okay, you calculate what is alpha. Alpha means for series circuit R by 2L, omega naught is 1 by LC. Okay, so all the values are 1. So alpha is 1 by 2, omega naught is 1. That means alpha is less than omega naught. Okay, this system is called underdamped. Okay, this system is called underdamped system. Okay, so option A is correct. Okay, so next question. Find the nature of the response. Nature of response. 5u of minus t 1 by 2 ohm 1 Henry 1 Faraday. Okay, so the options are given like that. First, what is the response of A? Is it underdamped or overdamped? Sorry, overdamped or critical damped? The A is called overdamped. B is critical damped. C is underdamped. D is undamped. Okay, again you come to the circuit. See, this is 5u of minus t. That means what? This source is active from minus infinite to the time up to 0. Okay, after t is equal to 0, okay, this value is 0. That means what? You know the function of u of minus t. Okay, what is the function of u of minus t? Okay, it will be having some value when the time is in between, when the time is negative, but once if we come to the positive time, the value is 0. That means what? This source is connected to the circuit up to t is equal to 0. After t is equal to 0, the source is disconnected. That means what? It is similar to having the switch here, exactly opening the switch at t is equal to 0. Okay, so switch is already closed, then you are opening the switch at t is equal to 0. That means what? After t is equal to 0, this is like a source free circuit. This is like a source free circuit. Okay, now and again here again see, once at t is equal to 0 minus, what is the nature of the circuit? Okay, at t is equal to 0 minus, okay, again at t is equal to 0 minus, the circuit is in steady state. Okay, so this is current source with the 5 ampere. This is one resistance. This is inductor. Inductor at steady state is short or open? Anybody?
Short, sir.
Short. Yes. Okay, so the capacitor is open. Okay, now now what is the energy in the circuit? Which element will be having the energy?
Capacitor. Inductor.
Capacitor. It's not a capacitor. The inductor will be having the energy, because the entire 5 ampere current will flow here, because this is really short, and again this is 0 volt only. Then the energy across the capacitor at t is equal to 0 minus is 0 only. Okay, so only the inductor will be having the initial energy in this case. Okay, the inductor will have initial energy. Okay, so in the previous case the capacitor is having the initial energy, but in this case the inductor is having initial energy. But no problem, either inductor or capacitor, but all the elements are in parallel only. So again you may have a doubt, why is there in the discussion you put here plus VC when I have a parallel case? Why you put V here? Because whether I put V here or here, no problem, all are same. Okay, so because when they are parallel, the voltage is same. So it doesn't mean that, okay, once if I put V here, doesn't mean that the capacitor is having initial energy, because this V is like a running variable. What would be the V with respect to time? That we are trying to analyze. That's it. Okay, so I am not telling the capacitor is having initial voltage. Okay, so in this case, which one is having the initial energy? The inductor is having the initial energy. The inductor is having initial energy. And also one more thing, once when we apply the Laplace transform, we have not taken into account the initial energy. Why? Anybody? See, when we write the Laplace transform, if the inductor or capacitor is having initial energy, we used to write like this. யாருக்காவது ஞாபகம் இருக்கா? Laplace transform apply பண்ணும்போது initial energy இருந்தா, we will put that initial energy also here. ஞாபகம் இருக்கா இல்லைங்களா?
Okay, sir.
ஓகே இல்ல, ஞாபகம் இருக்குங்களா இல்லையா? ஓகே.
Yes, sir. Yes, sir. Yes, sir.
Why ஏன் இந்த இடத்துல கரெக்டா நம்ம அதை போடல? யோசிச்சு பார்த்து சொல்லுங்க. ஓகே, எதனால போடலன்னு சொல்லுங்க. ஏன் நம்ம அந்த ஃபார்முலா இது போல வரும் மைனஸ் இனிஷியல் கண்டிஷன். அந்த இனிஷியல் வேல்யூவே இந்த இடத்துல ஜீரோவா இருக்கும். அந்த பர்டிகுலர் வேரியபிளுக்கு மேபி வோல்டேஜ் இருந்தா அந்த வோல்டேஜ் ஜீரோவா இருந்திருக்கும், கரண்டா இருந்தா அந்த கரண்ட் வந்து என்ன வந்திருக்கும்? ஜீரோவா இருந்திருக்கும். ஏன்னா நீங்க எடுத்திருந்தாலும் கரெக்டா தான் வரும். ஸோ ஃபார் எக்ஸாம்பிள் இப்போ இந்த கேஸுக்கே வரேன் நான். இந்த கேஸ்ல வந்து இப்போ இதுக்கு நம்ம எழுதும் பொழுது இதுக்கான வோல்டேஜ் என்ன சார் வருது? இனிஷியல் வோல்டேஜ் ஜீரோ தானே வருது. அப்போ அந்த ஃபார்முலால நீங்க அதை கொடுத்திருந்தாலும் அது ஜீரோ ஆயிட்டு இருக்கும். என்ன சொல்றேன்னு புரியுதுங்களா? ஜீரோ ஆயிருக்கும். ஸோ கரண்ட் இனிஷியல் கரண்ட் வருது, பட் அந்த ஃபார்முலால கரண்ட் வந்திருக்காது. கரண்ட் கேட்டிருக்க மாட்டாங்க இனிஷியல் கரண்ட். ஸோ அதை கொஞ்சம் யோசிச்சு பாருங்க. ஓகே, ஸோ in this case the inductor is having the initial energy. Okay, initial energy, but anyway, but we will operate with the formula. What is the formula? Alpha, okay, for a parallel RC circuit, that is 1/2 RC, where omega naught is 1 by square root of LC. Okay, so 1/2 R is 1/2, C is 1, then this value is 1, omega naught is equal to 1 by omega naught is equal to 1 into 1, and again omega naught is equal to 1. Okay, so alpha is equal to omega naught. That means when alpha is equal to omega naught, the damping is called critical damping. Critical damping. So critical damping means second one. Critical damping means second one. Okay, so with this I will stop. We'll see the remaining things, because these are a little bit maybe new to you, and or otherwise for newcomers, because they have not studied the control systems. Once if you have studied the control system, and this is really easy. But anyway, the same thing we'll discuss in control system also. Okay, so with this I will stop. Okay, so and again